Hi, everybody. My name is Jiaxin Qin. I'm with the Department of Information Engineering, the Chinese University of Hong Kong. The paper I'm going to present is titled Enhancing the Decoding Rates of Code by Learning with Guided Information. Before jumping into the code, let's review on the usage of a wireless multi-hop network. The wireless multi-hop network is an important network topology in modern wireless communication. It has wide applications in remote area communication, wireless sensor network, and 5G integrated access and backhaul system, which we usually call the IAB system. Wireless multi-hop network occurs in many real-world use cases where signals are transmitted and relayed through a large area. Especially as we move towards a 5G and beyond with gigahertz spectrum, the IAB system is playing an increasingly crucial role in relaying the wireless signal and connecting base stations. Because we all know that as the frequency increases, the wavelength decreases. In 5G, millimeter wave is usually used, which typically has a range of 300 meters, which is only 2% of 4G's range. And therefore, the IAB system, which relays the signal between different nodes, is becoming more and more important. The packet loss in wireless communication is inevitable due to congestion, fading, interference. It has a much higher channel loss compared with communication using twisted cable pair cable and optic fiber. However, the TCP/IP protocol stack is designed based on the assumption that the link layer communication is of both high reliability and low latency. Therefore, to satisfy the latency requirement of the TCP, the channel loss need to be kept under a certain threshold, for example, 1%. In order to satisfy such requirement in wireless communication, adaptive modulation coding, which we call AMC, is used. It basically reduces the coding rate and modulation rate, or increases the transmission power to keep the channel loss within the threshold. The issue with this scheme when it's used in a wireless multi-hop network is that as the number of hops increases, the overhead introduced by retransmission and AMC significantly limits the network throughput. For example, using IEEE 802.11a, under the same condition, if a single hop throughput is 20 megabits per second, the end-to-end throughput drops to around 1 megabits per second when the network has 8 hops. And obviously, a practical wireless multi-hop network may have more than just 8 hops. BATS code is an emerging network code that solves the low throughput problem in wireless multi-hop network. Taking advantage of the network coding and a bipartite graph-based design, the BATS code relaxes the need for low channel loss with a small and bounded overhead. It means that with a little actual cost, the BATS code can work with higher channel loss, for example, 10% in a wireless multi-hop network. So with the BATS code, the AMC can send data more aggressively using higher modulation rate and code rate, or using lower transmission power. And with the BATS code, we can even redesign a TCP. We know that if we send a file in TCP, the file will be segmented into several packets. And for each packet, we will need an ASIC to indicate that it is well received. Otherwise, this packet will be retransmitted. Since the BATS code is a rateless code, and so long as enough information is received at a destination, we can decode a transmitted file. We actually don't need an ASIC for every packet sent. All we need is one ASIC after the file is decoded at the destination. Therefore, the communication time is significantly reduced, and because there are less ASIC packets, the congestion and interference will be greatly improved as well. As we all know, the congestion and interference are among the major reasons for the packet loss in wireless communication. And this little cartoon here shows how the BATS code encode and recode and decode a file. Even though some packets are lost during the transmission, we can still recover the whole file so long as we have received enough information. Let's now have a look at the batch code in more details. The encoding can be represented by a bipattern graph. The circle here represents an input packet, which is usually called a variable node. The dashed square here represents a batch consists of several coded packets. A batch in a bipattern graph is usually called a check node. Like the LDPC, the encoding is based on the degree distribution. Suppose we want to encode a file, we first divide a file into equal length packets. Then in order to generate a batch, we first sample a degree dg from the distribution. Then we randomly select dg packets from the file and put them as a matrix, which we call bi. Then we form a coded batch xi by multiplying the bi with the matrix gi, which we call the generator matrix. Now let's have a look at recoding. In traditional networks, intermediate nodes only perform simple packet routing and forwarding. While in the batch code, the intermediate nodes performs a coding, which is called a recoding as well. What it does is that for received batch decoded as xi, we simply multiply it with a random full-rank matrix hi. So suppose A packets is received for this batch. Some packets might be lost during the transmission, right? Then the dimension of the hi is A by m, where the m is a batch size. And the recoded batch is of size pk by m. And we notice that by doing the recoding, the batch with lost packet is recovered to having the same number of packets. So by doing the recoding and recovering the lost packet, the packet loss will not be accumulated exponentially in the multi-hop network. Similar to LDPC, the decoding of a batch code is also based on a belief propagation decoding, which is an iterative graph-based decoding algorithm. As we have seen, each batch is generated by taking a linear combination of a subset of input packets. Therefore, each batch is associated with a set of linear equations with the input packets as unknown variables. And these linear equations can only be solved if and only if the rank of the batch is equal to the number of unknown variables associated with it. The BP decoding basically checks for decodable batches, and after the batch is decoded, its decoded packets will be passed to other associated batches as known variables. The BP decoding continues until either there is no decodable batch or all packets are decoded. As we have seen, the generic graph represent a graph generation algorithm is based on degree distribution and random sampling scheme. The random sampling is suboptimum as it ignores the internal correlations among different nodes in the graph. So we hypothesize that there exists a better scheme which considers the interdependency of the check nodes and the variable nodes at the same time. And by doing so, we can achieve a higher decoding rate with a smaller overhead, that is, fewer edges and check nodes in the graph. First of all, we formulate this problem as a multi-arm bandit problem where we aim to maximize the one-time reward from a batch code simulation system, which is called a batch black box. When the agent will input a bi-agency matrix into the simulation system. And notice that rather than using a two-steps graph generation scheme in a conventional method, we generate a graph as a whole. Namely, we generate a bi-adjacency matrix directly. To proceed with this problem, we propose to use a deep reinforcement learning model for the graph construction. And rather than a degree sampling plus packet sampling scheme, we generate the graph as a whole, namely generating the adjacency matrix representing the bipattern graph. And through a consistent learning and interacting With the simulation system, we learn to generate graph, which is sparse and generates high decoding rate. Our model consists of three major components: the agent, the credit, and a batch black box. The agent is a deep learning-based model. It takes in a random vector and outputs a bi-adjacency matrix, which represents a bipartite graph. The credit is also a deep learning model. It basically judges the performance of the agent. It takes in a bi-adjacency matrix, which can either be generated by the agent or by other means. It outputs a single value, which in the literature we call Q value. The batch black box is a batch code simulation system. It takes in a bi-adjacency matrix and simulates the batch code according to the bi-adjacency matrix and other configurations. It outputs a reward proportional to the decoding rate and related to the graph sparsity. Training of this model consists of three steps. First step, we need to generate the training samples. The agent produces the bi-adjacency matrix and get a corresponding reward from the batch black box. Then we save the bi-adjacency matrix reward pair in a component called a replay memory. The second step is a credit update. The credit randomly samples the adjacency matrix reward pair from the replay memory and use them as a training input and label. The third step is the agent update. The agent produces bi-adjacency matrix and output to the credit. The training optimizer then tries to maximize the output of the credit. Basically, through the active interactions among the three components, the agent aims to produce an adjacency matrix that maximizes the Q value. The credit aims to generate a Q value that is close to the actual reward. And in order to get a better training convergence, we use other techniques to provide guidance to the training. Firstly, we use the graphs pre-generated by the conventional method as guiding samples. We put them in the replay memory in advance such that this model can learn from this experience. Secondly, we design a mechanism called a side information passing to improve the accuracy of the credit. The idea is that in a graph, there are some features known to us that are important for the decoding rate, such as the degree of the variable node and the degrees of the check nodes. So instead of completely relying on a deep learning model to learn these features, we manually pass these features to the last layer of the credit. In this way, the credit will have a more explicit and useful features to make decisions. We used two metrics for evaluation. One is the decoding rate, which is a percentage of decoded packets. Another one is a edge efficiency. It is the average number of decoded packets per edge. So higher edge efficiency means a higher coding efficiency. Then we tested our model against different number of hops and different number of batches. The orange line here indicate the proposed reinforcement learning method, and the blue lines here indicate a conventional method. As we can see, the orange line here outperforms the blue lines in general, and it has a more stable performance as the number of hop increases. Also, the orange line reached a decoding rate at around 1 at around 12 batches when it has 12 batches. And the conventional method reached the same decoding rate at around 16 batches. And this figure here shows the same result with a smaller batch size. And here shows an example of the output from the agent before the quantization. So in summary, we show that how to use the deep reinforcement learning in the code constructions, and we show its ability of capturing the special graphical structure of a good code by interacting and learning with the code simulation system. For future research directions, we hope to develop a more practical paradigm where the model can adapt to the changing channel conditions. Thank you for listening.